Welcome to our deep dive into LLM evaluation and optimization. In this video, we'll explore how to monitor, optimize, and tune large language models for production use. From understanding key metrics to leveraging advanced frameworks, you'll gain practical insights for improving your AI systems. Whether you're a developer, data scientist, or product manager, mastering these concepts will help you build more reliable, efficient, and cost-effective LLM application. Let's start by setting the stage for why evaluation and optimization matter in the fast-evolving world of AI. One of the most powerful tools in LLM evaluation is the concept of LLM-as-a-Judge. This approach uses a high-capability model like GPT-4 to grade the outputs of another model based on explicit rubrics. It automates subjective evaluation, such as tone and helpfulness, and correlates well with human judgment. However, it's important to note the trade-offs. While highly scalable, it can be expensive and may inherit biases from the evaluator model, including self-preference bias. Understanding these pros and cons is crucial for designing robust evaluation pipelines. Retrieval augmented generation, RAG pipelines require careful validation. The RAG Triad measures three specific dimensions: context relevance, groundedness, and answer relevance. Context relevance checks if the retrieved information matches the user query. Groundedness ensures the LLM's response is supported only by the retrieved context, avoiding hallucinations. Answer relevance confirms the final response actually addresses the user's initial question. These dimensions help ensure your system delivers accurate, trustworthy answers. Your LLM outputs structured data, such as JSON or SQL code. Evaluation splits into syntactic and semantic checks. Syntactic evaluation ensures the output can be parsed, for example, using JSON loads or a pedantic model. Semantic evaluation goes deeper. For SQL, you execute it against a test database and verify the schema matches expectations. For JSON, you validate keys against an absolute schema. This dual approach guarantees both format correctness and meaningful content. Latency is a critical factor in LLM applications, especially for user experience. The main metrics to track are TTFT time to first token, TPOT time per output token, and total latency. TTFT measures how quickly users see the first response, which is vital for engagement. TPOT tracks the speed of generation once the response starts. Total latency covers the entire round-trip time. Monitoring these metrics helps you identify bottlenecks and optimize your system for speed. Reducing time to first token (TTFT) is essential for responsive LLM applications. You can implement streaming with server-sent events (SSE), use semantic caching for repeated prompts, and leverage inference engines with prompt caching enabled, such as vLLM. Choosing smaller, distilled models also helps. These strategies ensure users receive answers quickly, improving satisfaction and engagement. Prompt caching is a powerful optimization technique. It retains the KV cache of long static prefix blocks, such as massive system prompts or fixed context documents, in GPU memory. When subsequent API calls use the same prefix, the system skips processing those tokens, significantly reducing latency and lowering costs, sometimes by up to 50%. This method is especially effective for applications with repetitive or static prompts. Semantic caching intercepts a user prompt, converts it into a vector embedding, and checks a vector database for highly similar prompts. If a match is found, the cached answer is returned instantly, bypassing the LLM entirely. This approach uses tools like Readiness or Pinecone and relies on cosine similarity greater or equal to 0.95 to identify matches. Semantic caching dramatically speeds up responses and reduces computational costs. Quantization shrinks the precision of model weights to save VRAM and boost throughput. FP16 offers high-fidelity precision and maximum accuracy, but demands heavy resources. INT8 provides 50% memory savings with negligible accuracy loss. INT4 delivers extreme memory savings, enabling massive models on smaller GPUs, but can introduce noticeable degradation in complex reasoning or formatting tasks. Choosing the right quantization method depends on your application's needs and resource constraints. ELEU and Rouge scores are traditional metrics for evaluating generated text based on n-gram overlap with reference answers. However, they fall short for modern LLMs as they don't capture semantics. A model can generate a factually identical response using synonyms, yet score 0 if there's no n-gram overlap. For LLMs, more advanced metrics are needed to assess true answer quality and relevance. Setting up an evaluation dataset or gold standard dataset is foundational for LLM benchmarking. Collect 100-500 diverse, representative samples of user inputs. Handcraft or meticulously review ideal responses as ground truth. Label metadata such as intent, category, and complexity to enable segmented regression testing during prompt or model upgrades. This process ensures robust, reliable evaluation and continuous improvement. RAGAS and TrueLens are open-source frameworks for LLM evaluation. RAGAS focuses on automated metrics using LLM-as-a-Judge, especially for RAG pipelines, measuring faithfulness and answer relevance. TrueLens introduces feedback functions that track safety, moderation, and performance, integrating directly into live tracing apps. Choosing the right framework depends on your evaluation needs and workflow integration. Token costs can add up quickly in production LLM applications. To optimize without switching to a cheaper model, trim system prompts, enforce max token constraints on outputs, condense or summarize context windows dynamically, and use few-shot examples sparingly. Once a model is fine-tuned, you can trim out few-shot examples entirely. These strategies help control expenses while maintaining performance. Batch inference aggregates multiple independent LLM requests and runs them through the GPU pipeline simultaneously. This maximizes GPU utilization and significantly reduces per token costs, often by up to 50%. However, it increases latency, making batch inference ideal for offline processing rather than real-time chat applications. Use batch inference for tasks like bulk document analysis or large-scale data processing. Pairwise evaluation is a robust method for comparing two models, such as after updating a prompt. An LLM-judge receives the user prompt alongside both outputs, presented anonymously and in random order to prevent bias. The judge declares which output is superior based on specific guidelines, avoiding absolute rating drift. This approach helps you make objective decisions about model improvement. eSpy revolutionizes prompt optimization by replacing manual engineering with programming. You define a declarative pipeline using signatures and modules. dSpy compiles the system, automatically optimizing prompts and selecting few-shot examples based on a metric you want to maximize. It behaves like a compiler optimizing software code, streamlining the process and improving performance. For enterprise applications handling millions of queries, cost optimization is critical. Use tiered routing, send routine queries to cheap, fast models, and escalate complex requests to advanced models. Analyze query intent to determine routing. Combine this with aggressive semantic and prompt caching to further reduce costs. This approach balances performance, speed, and expense at scale. Prompt injection is a security risk where untrusted user input manipulates the LLM system instructions. For example, a user might instruct the model to ignore previous instructions and reveal sensitive information. To evaluate vulnerability, use automated adversarial testing, such as red teaming with prompt fuzzers or tools like LangGraph. Regular testing helps safeguard your system against malicious attacks. Token allocation differs between open-loop and closed-loop generation. In open-loop, the prompt is sent and the model outputs a response without monitoring until completion. Closed-loop generation evaluates tokens dynamically during generation or across small substeps, allowing early termination if the model shifts off-topic or triggers safety blocks. Closed-loop offers more control and safety for production system. Reference-free metrics judge the quality of LLM responses without needing a pre-written human answer. Examples include evaluating politeness, coherence, or toxicity using classifiers or generic LLMs. These metrics are useful for automated evaluation, especially when human reference answers are unavailable or impractical to generate. Temperature setting in LLMs affects response randomness and evaluation reliability. Higher temperatures introduce more variance, making deterministic evaluation volatile. For reliable benchmarking and automated testing, set temperature to 0 to ensure reproducibility. This practice is essential for consistent, trustworthy evaluation results. Cost monitoring is a continuous process in LLM applications. Track token usage, API call frequency, and model selection to identify expensive operations. Use dashboards and analytics tools to visualize spending trends. Regular reviews help you spot inefficiencies and adjust strategies, ensuring your AI system remains cost-effective. Latency tracking involves measuring response times at various stages of LLM processing. Use tools to monitor TTFT, TPOT, and total latency. Analyze logs to identify slowdowns and optimize infrastructure. Fast, predictable latencies are key to delivering a seamless user experience and maintaining high engagement. Prompt tuning is an iterative process to improve LLM performance. Experiment with different prompt structures, adjust system instructions, and test few-shot examples. Use evaluation metrics to measure impact and refine prompts. Prompt tuning helps you achieve higher accuracy, relevance, and user satisfaction. Segmented regression testing uses labeled metadata in your evaluation dataset to test specific segments, such as intent categories or complexity levels. This approach allows targeted analysis during prompt or model upgrades, ensuring improvements benefit all user groups. It's a powerful tool for maintaining balanced performance. Automated adversarial testing, such as red teaming, is essential for identifying vulnerabilities like prompt injection. Use prompt fuzzers and specialized tools to simulate attacks and evaluate system resilience. Regular adversarial testing strengthens your LLM application's security and reliability. TrueLens introduces feedback functions that measure safety, moderation, and performance in LLM evaluation. These functions integrate directly into live tracing apps, providing real-time insights. Feedback functions help you monitor and improve your system's behavior, ensuring compliance and user safety. RAG uses the faithfulness metric to evaluate whether LLM responses are grounded in retrieved context. This automated metric, powered by LLM-as-a-Judge, ensures answers are accurate and supported by source data. Faithfulness is crucial for building trustworthy RAG pipelines and avoiding hallucinations. Answer relevance is another key metric in RAGAS, measuring whether the LLM's response actually addresses the user's initial question. Automated evaluation ensures responses are not only accurate but also relevant, improving user satisfaction and system reliability. Safety and moderation metrics are vital for LLM evaluation, especially in production environments. Use classifiers or feedback functions to detect toxicity, bias, and inappropriate content. Regular monitoring ensures your system remains safe and compliant with regulations. TrueLens enables performance tracking by integrating feedback functions into live tracing apps. Monitor response times, accuracy, and user engagement in real time. Performance tracking helps you identify areas for improvement and maintain high-quality LLM applications. Effective token allocation is essential for optimizing LLM performance. Use max token constraints, dynamic context summarization, and prompt trimming to control output length and costs. These strategies ensure efficient resource usage and maintain response quality. Few-shot examples help guide LLM responses, but they can increase token costs. Use them sparingly and remove them once your model is fine-tuned. This approach balances guidance with efficiency, ensuring high-quality outputs without unnecessary expense. Dynamic context summarization condenses input windows before feeding them to the LLM. This reduces token usage and speeds up processing. Use summarization algorithms or manual review to ensure essential information is retained, optimizing both cost and performance. Maximizing GPU utilization is key for efficient LLM processing. Use batch inference to aggregate requests, optimize model quantization, and monitor resource allocation. These practices reduce per-token costs and improve throughput, especially in high-volume environments. Selecting the right quantization method depends on your application's accuracy and resource requirements. FP16 offers high accuracy but uses more memory. INT8 balances memory savings and accuracy. INT4 provides extreme savings but may degrade performance in complex tasks. Evaluate your needs to make the best choice. Streaming responses using server-sent events (SSE) allows users to see answers as they're generated. This improves perceived speed and engagement. Implement SSE in your LLM application to minimize TTFT and deliver a more interactive experience. Semantic caching uses vector databases like Readiness or Pinecone to store embeddings of user prompts. When a similar prompt is detected, the cached answer is returned instantly. This technique speeds up responses and reduces computational load, making your LLM application more efficient. Prompt caching stores static prefix blocks in GPU memory, allowing repeated API calls to skip token processing. This reduces latency and lowers costs, especially for applications with fixed context documents or system prompts. Use prompt caching to optimize performance in high-frequency scenarios. Tiered routing sends routine queries to cheaper, faster models and escalates complex requests to advanced models. Analyze query intent to determine routing, combined with semantic and prompt caching for aggressive cost control. This strategy ensures efficient resource allocation and maintains high-quality outputs. Adversarial testing tools like GRAC and prompt fuzzers help evaluate your LLM system's vulnerability to prompt injection. Simulate attacks and monitor system responses to identify weaknesses. Regular use of these tools strengthens your application's security and resilience. Closed-loop generation allows early termination if the LLM shifts off-topic or triggers safety blocks. Monitor tokens dynamically and stop generation when necessary. This approach prevents unwanted outputs and maintains system integrity, especially in sensitive applications. Classifier-based evaluation uses purpose-built models to assess LLM responses for attributes like politeness, coherence, and toxicity. These classifiers provide automated, scalable assessment without needing reference answers. Integrate classifier-based evaluation for efficient quality control in large-scale deployments. Reproducibility is vital for reliable LLM evaluation. Set temperature to 0 during benchmarking and automated testing to minimize randomness. Document evaluation protocols and use consistent datasets. These practices ensure your results are trustworthy and comparable across iterations. Summary: optimizing and evaluating LLMs requires a blend of technical strategies and robust frameworks. Monitor costs, track latencies, and tune prompts for performance. Use advanced metrics, automated testing, and tiered routing to balance quality and efficiency. By following these best practices, you'll build AI systems that are reliable, scalable, and cost-effective. Thanks for joining this journey into LLM evaluation mastery.